Hello and welcome. In this tutorial, we will learn about functions in Python, so let's get started. So far, we have used many functions such as len, print, min, max, etc. The reason why they are called functions is that they are used to perform a specific task. Generally speaking, a function takes an input, process it and provide an output dictated by the inner algorithm of the function. Let us take an example with the function len. The len function takes a sequence as input such as a list, and outputs the number of elements in the sequence. Now, the question is, how does the len function count the number of elements in a sequence? There is a hidden code inside this len function which does this operation. This block of code resembles the operation done by the len function. That is, the code you do not see behind the len function. The highlighted block in the second code block represent the operation done by the len function. First, we need to create a variable called length and assign a 0 value to it. This will be used as a counter for the number of elements in the sequence. Then, the for loop will be used to iterate over every element in the fruits list and increment the value of length variable by 1 once a single iteration is done. Since the for loop accesses the sequence till all elements are iterated over, the length will be incremented according to the number of elements in the sequence, and the final result of the length variable will be the length of the sequence. Finally, you can print the length variable to check your answer. Now, let us take another example explaining the sum function. The function sum takes a sequence of numbers as an input and outputs the sum of all elements in it. The list of numbers is saved in a variable called numbers, and the add variable is the sum of numbers in this list. In order to replicate the inner working of the sum function, we first need to create a variable called add which will be used to sum over all numbers in the list. The starting value should also be initiated to 0 to have a correct summation. Then, we need to iterate over all numbers in the list and increment the add variable by the current number in the list. When the for loop iterates all elements in the list, the add variable will have the sum of all numbers in the list. Finally, you can print the add variable to check your answer. Now, suppose we have 3 lists of numbers that we would like to check the summation of. Doing so with the replication method forces you to have replicate code to perform the same operation for each list. Therefore, you will end up with writing 3 for loops to check the summation of all elements inside the lists numbers 1, numbers 2, and numbers 3. As you can see, this is not quite nice looking piece of code as we have 3 different loops that does the same thing. The situation can get worse when you have larger number of sequences to check for. This problem is solved by creating custom functions in Python. Now you might be wondering, why do we need to use function if we can create its inner operation of the same function? There are 2 main valid reasons to do so. First, you do not need to replicate a code that is already implemented, which allows you to save time to carry on with your projects and perform the operation that you need. This will make your code easy to understand and even more readable. Second, as you have seen in the sum example, you must replicate the code for every sequence every time you have a new sequence. This is totally not practical. To solve this problem, we will define a function with inner operation or algorithm to perform the summation, without the need to have a separate code for each list of numbers. But before that, let us study the syntax of functions in Python. Here is the syntax to create a custom function from scratch. The def keyword is used to define a function creation. FunName is the function's name, by which the function can be called to perform the operation coded in the body of the function, which is the expression or algorithm. Arguments are the input values to the function, which will be processed by the function's body to return an output value. Similar to loops in Python, there should be indentation after defining a function. Now, let us build a function called SumElements to perform the summation over all elements in the list. As you can see, we are defining a function called SumElements, which takes a variable called numbers as input argument. Numbers variable should contain a sequence of elements such as a list. The body of the function is similar to what we have previously seen to replicate a summation over all item in a sequence. The function returns the add variable as an output, which equates to the sum of all elements in the numbers variable. It is important to note that a function does not work by itself. In order to use the custom-built function, you need to call it and assign an input argument in order to get an output from it. Now let's see how it works in a code example. In this code example, we are first identifying our algorithm in a function called SumElements, which adds all elements inside of a sequence represented by the numbers variable. Then, we are defining the lists whose elements will be summed using the SumElements function. Lastly, we are calling the SumElements function to sum the elements for each list. Numbers 1, numbers 2 and numbers 3 lists are the input arguments, and sum1, sum2 and sum3 are the returned output for each list when the SumElements function returns the add variable. Notice that for each list, we are calling the same function to perform the element-wise addition every single time. In this case, we are avoiding writing multiple loops that does the same operation, as we have previously done just by calling the custom-built function, which was only defined once. So far, we have demonstrated the importance of using functions, and we saw that we can pass an input to the function and return an output from the function. Functions are really flexible in that you can also have multiple input arguments and returned outputs. There are 3 main types of function input arguments that you can implement in Python. We will learn about positional and keyword input arguments, default input arguments, and arbitrary input arguments. Now, let's begin with the first type of function input argument. We will do so by creating a function that divides 2 numbers. The function name is divide and it takes 2 input arguments a and b. The function returns the value a divided by b. As you can see, we are able to pass 2 inputs and return a single output. If you assign variable a with value 4 and b with value 2, then the function returns 2. Now, let us swap the input values so that variable a has value 2 and b has value 4. Then, the function returns 0.5. This way of defining input arguments is called positional arguments. In positional arguments, the order of input arguments makes a clear difference in the function's returned values, because the first argument always follows the first parameter, and the second argument always follows the second parameter, and so on. Now, when you have a large code and potentially more function input arguments, it is difficult to remember how to place the order of parameters to match the intended order of the input arguments. In this case, you can use the keyword's input argument technique. So, let us see how to use the keyword arguments technique and apply to the same divide function we already created. Instead of just passing the input arguments to the function as in positional arguments, here we specify the value by assigning it to the input argument a and b variables. In this way, interchanging the position of a and b when calling the function does not matter anymore since each input argument has a specified variable name with assigned value, no matter what. Another way to handle input arguments is by using default input arguments. This type allows you to have optionally changeable default value which is always passed to a function when calling it. This is the syntax of the default input argument. Notice the addition of the new var in the function definition with a value assigned to it. Let us understand it by an example. We will modify the function divide such that the value of variable a is always divided by 2 as an example. To do so, we are creating a default value of b that is equal to 2. In this case, you do not need to specify the value of b when calling the function. Notice that the function definition has only a single positional argument which is variable a. Therefore, you only need to specify a single value when calling the function divide. It is important to not confuse keyword input argument with default input argument. Keyword input argument's value is created when you call the function. However, the default input argument value is created when defining a function. It is important to note that the default value can be modified in the function call using a keyword input argument, although it had an assigned value in the function definition. In the first code line, we are passing a positional input argument value of 2 for argument a, and the default input argument b is changed from default value 2 to value 4 in the function call as a keyword input argument. The default value remains as integer value 2 no matter what since the function was defined with this value. The default value change in the function call is temporary for this function call only. The output of the code shows a correct value that is 0.5. In the second example, we are passing the first argument a is a keyword input argument along with adjusting the default value of b into a new value. We previously built a function to sum numbers in a sequence. This function takes a single argument with list data type to add its all elements to a variable called add. The list that is passed to the sum function should already be defined before calling the sum elements function. Therefore, there is a well-defined number of elements in a list prior calling the function. But what if in a case where you do not know the number of elements and values of a list up front? This is where you use arbitrary arguments which will allow you to pass any number of positional input arguments. Arbitrary positional input argument is defined with an asterisk before the input argument name. With this technique, you do not need to predefine a list in this case. The collection of arbitrary arguments will be passed as a tuple and be saved to the arbitrary variable defined in the function, so you can still use a for loop to iterate over the arbitrary positional input arguments. In this code example, we are defining the same SumElements function which adds all elements in a sequence. Notice the arbitrary positional input argument is defined with an asterisk. In the first line of function definition, we are printing the type of the input argument to prove to you that arbitrary definition of the input argument converts the input to an iterable data type that is a tuple. Since the input becomes a tuple object, its elements can be iterated over and all elements will be added using a for loop. In the second printing function, we are printing the numbers variable to show you the values of the tuple. The function returns the add variable which holds the addition of all elements in the tuple. Then, we are calling the function with just 4 inputs with integer data type. As you can see in the output of the code, the print functions print the type of the input as a tuple and its values. Next, the output displays the addition of all elements. The output value is 10. Now, what if you input 8 elements instead of just 4? As you can see, the output value is updated to 36 as per the addition of all 8 new elements in the input. Therefore, you can have any random number of inputs when defining the arbitrary arguments without knowing the number of elements up front. The same concept can be applied to arbitrary keyword input argument, so let's check it out in the next section. The concept of arbitrary keyword input argument is the same as the concept of arbitrary positional input argument. However, there are two main differences in the syntax and data type. First, you need to have 2 asterisks to define the arbitrary keyword input argument. Second, the data type of the arbitrary keyword input argument is a dictionary, not a tuple. So, let's take an example to understand it. In this code example, the input argument is defined with 2 asterisks to form an arbitrary keyword input argument. First, we are calling the SumElements function with just 2 keyword arguments. In the first 2 lines of code in the function definition, we are printing the data type of the input argument, and then printing the input itself. As you can see in the output of the code, the data type of the variable numbers is a dictionary. This is evident when print the variable numbers itself. Notice in the second line of the output code that the keys of this dictionary are set according to the name of variables in the arbitrary keyword input arguments, and the dictionary values are set according to the values of the arbitrary keyword input arguments. Now, in order to add all the values in the numbers dictionary, we need to adjust the loop such that we loop over each key in the dictionary and sum the corresponding value in the key value pair to the add variable. Then, the function returns the add variable. Now, let's add more arbitrary keyword input arguments to see what happens. As you can see in the output of the code, the numbers dictionary is updated with the new values, and the sum values now is equal to 10. So far, we have seen how to deal with input arguments of Python functions. So now we will see how to deal with functions output or the return values. Throughout the examples we have seen so far, we were able to only return a single value from a function. However, there are more techniques and options to return a value from a function. There are 4 different scenarios of returning values. You can return a single value or multiple values, return multiple values as a single object, return a value based on conditional statements, or lastly you can have a function that returns no value. So let's study each one of them. Suppose you want to build up a function that returns the attributes of a list of numbers. Those attributes will be sum of all elements in a list, minimum value, maximum value, and average. Therefore, we need to build up a function that returns 4 values. This is the syntax to return multiple values from a function. Depending on the number of returns from a function, you need an n number of variables to receive the values returned from a function. Each variable var in the syntax must be separated by a comma. Now, let's see how to implement it. The sum part is similar to what we previously implemented. It does so by using a for loop. Next, the min function returns the minimum value in the list and saves it to the list min variable. Then, the max function returns the maximum value in the list and saves it to the list max variable. Lastly, the average of the list is the sum of all elements divided by the length of the list. The average of the list is saved into a variable called mean. Because the function has 4 outputs, then you need 4 variables to save those outputs and must be in order as per the function definition of the returns. Since the function return the sum value first, then the first variable assignment must be some value in this case. Similarly, since the second value that the function return is min value, so the next variable assignment must be min value, and so on. You can have any variable names as long as they make sense of what they are being assigned to. For example, the list min contains min value, list max contains max, and mean contains average value. In this way, it is easy to differentiate between the output variables and remember the meaning of each variable. In the previous section, we have seen that we need n number of variables when having multiple returns in the function definition. Now, we will learn how to return multiple values in a single object. There are 2 ways to do it. Either you return the multiple values as a tuple object, or any other data type. Let's see how to do it. Here, we have the same code example to return the attributes of a list. Also, the function definition returns the same variables in order as we have done before. However, notice the difference is that we are assigning all return values to a single output variable called attributes, instead of 4 variables as we have done before. When returning multiple values to a single output variable in this way, the data type of the output variable will always be a tuple. As you can see in the output of the code, we have obtained similar values compared to the previous section. However, those values are contained in a tuple object. Then, you can access those values by tuple slicing or using an index as we have done in the tuple section. In the second technique, we are modifying the way the function returns the multiple values in the function definition. Instead of returning 4 different values, we compressed everything in a single object. A list in this case, just as an example. Still, you can join those values in a different data type as you wish. Notice the output of the code. The attributes variable is a list data type as per the function definition of the return values. Another option to return a value from a function is by using conditional statements such as if-else statements. In this code example, we have a function that adds or subtracts 2 numbers a and b based on input Boolean argument variable called doSum. DoSum variable can be set to true to perform summation, or false to perform subtraction. As you can see, when doSum is true, the function returns a plus b, but when doSum is false, the function returns a minus b. In the first example, we set the values of a to be 4, and the value of b to be 3, and the doSum variable is set to true. As you can see in the output of the code, the resulting value is 7, which means that the return a plus b is the one that was accessed in the if-else statement. In the next example, a and b have the same values, but the doSum value is set to false. Therefore, the second return is accessed and the output result is 1. It is possible in Python to define a function with no return value. In this code example, we are performing the same previous example, But we are just printing the value a plus b or a minus b depending on the value of do-sum variable, instead of returning them as function output. In future practice notebooks and future courses, you will see more details about when it is necessary to avoid having function returns. So far, we have studied the types of functions' input arguments. However, in the most general syntax of functions, you can use all types of arguments to define a single function if your application requires so. Therefore, you can have a function with positional arguments, arbitrary positional arguments, default arguments, and arbitrary keyword arguments. In the case when you need to use all types of arguments in a single function, then you must follow the order of arguments to have a correct syntax. Furthermore, the function's return can also have various forms such as returning single value or multiple values as a single object, return values based on conditional statement, and you can also have a function with no returns. Note that it is possible in Python to build up a function that have both input arguments with return values, or input arguments without return values, or return values with no input arguments, or a function that lacks any input arguments nor return values. We will see too many examples in the future for each use case. In the previous example, we learned that we can build a function that can optionally take input arguments and returns no value as in the print function case. We mentioned that the add or subtract function returns no value but just prints the summation or subtraction value using the print function. This is not quite an accurate statement. In fact, the function does return an output which is the none data type. None, just like other data types such as integers, floats and strings, it belongs to data type called none type. As you can see in this code example, we are calling the add or subtract function and assigning it to variable x. Then, we are printing the value of x and the type of x, as you can see in the output of the code. The integer value 7 is obtained from the print function as per the function definition. Next, we are printing the value of x, which shows a none value. The function returns none because there was no real returned output to print such as integers, floats, strings, etc. Next, we are printing the type of variable x, which shows that the none value belongs to the none data type called none type. Therefore, a function will allow to return none value when there is no return statement in the function. In a nutshell, the none is used to define null values in Python. Assigning a none value to variable is a way to reset it in the sense that it brings it back to an empty state with an absence of value. Very often, you will use none to define a default function input argument for an optional parameter, and there is a significant reason for it, so let us see it by an example. Suppose you are building a function called appendItem that appends a new value called newElement to a list called oldList. The oldList has an empty list as default value. When you append an element to the oldList, the code works as expected and the new element is appended as you can see in the output of the code. Now, what if you add a new value to the default oldList value which is just an empty list? You will think that every time you call the appendItem function, you will append a new element to an empty list every code run. But unfortunately, the code does not run as expected. So in the first line of code, we are appending integer 1 to an empty list. As expected, integer value 1 is appended to an empty list as shown in the output of the code. Now, we are calling the appendItem function again to append integer value 2 in the second line of code. As you can see in the output of the second code, the integer value 2 was not added to an empty list, but it continued building up on values from previous code run, although the default value of the old list is an empty list. It was supposed that integer value 2 be added to an empty list, but it did not. Next, if you call the append item function again to append integer value 3 to the list, you will notice again the unexpected behavior in that the integer value 3 was added to a list with elements obtained from previous code runs. Although the default value for the old list is an empty one, the append function will always build on old code runs. Therefore, this code does not run as expected. There is a reason why lists act this way, and we will study it in the next section. Now, it seems that the list keeps on updating on top of the old values, so we need to force it to start from empty list every time the user does not pass a list, instead of the default value in the second argument of the function definition. To do this, the default value of old list variable must be none. This means that this variable is instantiated with an empty state and not defined as a list or any other data type, except none type. The reason we do this is that if the user does not change the default value of old list variable, the if statement is true, and the old list variable is replaced by an empty list instead of none. Therefore, every time the user calls the function without changing the default value of old list variable, the old list variable will always be instantiated with an empty list, and this results in single value appended to the list. Now, in the first line of code, we are only passing an integer value 1 to be appended to the old list. Since a list was not passed in the second input argument in the function call, the if statement condition returns true, and the old list value is set to an empty list. Therefore, the new element integer 1 is appended to an empty list. Next, in the second line of code, we are trying to append integer value 2 to the default value of the old list variable. Since a list was not passed in the second input argument in the function call, the if statement condition returns true, and the old list value is set to an empty list. Therefore, the new element integer 2 is appended to a fresh empty list. In this case, adding new elements to a list does not build up over subsequent runs due to the condition of the none in the if statement, which forces the old list variable to start from an empty list when the user does not pass a list in the second argument in the function call. Next, we are trying to append integer value 4 to a list of integers 1, 2, and 3. In this case, the default value of old list is changed from none to a user-defined list in the function call. Therefore, the condition in the if statement is false, and the new value is appended to the user-defined list as usual. Throughout many examples we have done so far, we created variables defined inside and outside of functions. However, have you wondered how variables defined inside and outside of functions are related? Let us see an example. We have a function called multiply which returns a value a times b and assign the result to variable y. If you call the function with inputs 2 and 2, the function returns y as equal to 4. However, if you print y outside the function, you will get an error message which mentions that y is not defined. Although y is defined inside the function, it is still not recognized outside of it. The reason behind this is called Python scope. Python scope is a case in which a variable is only available and defined inside of the region it was created in. Therefore, we got an error message saying that y was not defined since it was only defined inside of the function multiply. Python only temporarily saves variables defined in a function and deletes it after the function execution. Therefore, in general, variables defined inside of functions are not related to the ones defined outside. even if those variables have the same variable name. Variable deletion after function execution only happens for variables defined inside of functions. For example, if we assign the return value of the multiply function to a variable y outside of the function, the variable y will always hold its value. The variable y defined inside the function and the one defined outside the function are again not related, due to the memory isolation between function definitions and the main program. The variables defined in the main program are called global scopes, and the variables defined inside the functions are called local scopes. The main benefit of memory isolation is that variables with similar names but defined in different scopes do not overwrite each other, which makes coding and debugging easier. There are two specific cases where global scope can get affected by local scope, meaning that variables defined in function definitions do affect variables defined in the main program. Those cases are when variables are assigned with lists or dictionaries. We previously examined this example code when we studied the none data type. The append item function appends new element to the local list variable. The local list variable is set to empty list value in the function definition as a default value, but you can pass any list if you wish. Now, we are defining a list called global list outside the function definition, so it is a global scope. Then, the append item function is called with a new element value equal to 4, and the global list variable as a second input argument instead of the default empty list definition in the append item function. The return value of this call is assigned to a variable called new list, which should get the same list as global list variable, but with the new element 4. Next, we are printing the value of the global list and new list variables in order to see what happened to them after calling the append function. As you can see in the output of the code, the value of the global list has changed, although the return value of the append item function was not assigned to it, but to the new list variable. This means that local scope modification of the list affected the global scope of the same variable. This is why we used the none data type in the previous section to correct this wrong behavior. Therefore, you have to be careful when dealing with a list or a dictionary defined inside of functions. But why modifying lists and dictionaries in local scope affect global scope while variables with integers, floats, strings, booleans and tuples values get the benefit of memory isolation between main program and function definitions? This is because lists and dictionaries are mutable while other data types such as integers, floats, strings, booleans, tuples are immutable. As a reminder, mutable object is the one can be updated or modified after being created. Let us see it through this example. Suppose you have a variable x with integer value of 2. In this case, the variable x acts as a pointer to the value 2. Therefore, if we increment the value of x by 1 to be 3, then we are actually not updating the integer value 2, but we are changing the pointer from integer 2 to integer 3. However, in the case of a list or a dictionary, updating their values does not change the pointer to a new value, but you are adding a new element into the same object itself to which it was originally pointing to. Inner function is a common practice implemented by using functions within other functions. There are many benefits to do so, and the main one is function reusability rather than creating a single big function that only performs one purpose. Let us see an example.
1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1.
We previously created a function called listAttributes which returns the sum, min, max, and mean of a list of numbers. The function has 4 parts each of which calculates a list attribute. Now, the 4-part attributes code that are presented here only work with this function definition, meaning that the sum is only obtained when you call the listAttributes function. However, in many cases, the sum functionality is not only used to get list attributes, but also used in many other code implementations. Therefore, it does not make any sense to keep calling the listAttributes function just to get the sum. In this case, you can make the sum as a separate function which can be used not only in the listAttributes function, but it also can work in other part of codes. Also, the same concept applies to the average calculation, so the mean will have a separate function as well. As you can see in this code example, not only does the listAttribute function depend on the sum, but also the mean which calculates the average of the list. The getSum function can also be used in another function called getMean to get the average of the list. This is done by calling the getSum function inside of the getMean function divided by the length of the list to return the average. In a nutshell, we are breaking down the big function into smaller pieces, so that some functions could be used inside of other functions for code reusability purpose. So far so good, we have learnt many aspects of functions, but you have to be careful when naming them. In Python, there are many built-in functions such as the len, which calculates the number of elements in an object like strings, tuples, lists, dictionaries, etc. Also, we have the min and max functions which return the minimum and maximum values in a given sequence of numbers. There is also the Python built-in sum function to add up all elements in a sequence. We previously created a function also called getSum which does the same thing. It adds all elements in a sequence. Even if both have the same functionality, it is advisable not to name the custom-written functions similar to the built-in ones, as the custom functions will overwrite the built-in ones, meaning that Python will execute your custom function instead of the built-in function when you call it in a code line, if both have the same name. Furthermore, it is advisable to use built-in functions whenever possible in order to avoid wasting time recreating existing ones. We custom developed the getSum function which does the same thing as Python built-in sum function just to inform you how it works.